Once
Satellites collecting weather data 24 hours a day. But it isn't just for weather forecasts. Governments are worried by the idea that we, humans, are changing not just the weather, but the global climate. They're funding massive research programs. Can we really affect the climate system? Are we causing this?
With winds gusting at nearly 90 miles an hour, London has suffered some of the worst devastation since the hurricane 2.5 years ago.
The Pacific waves destroyed the beachfront, undermining...
How could we influence global climate? More to the point, how can we possibly know if we are or not?
Climate system is complex. It spans the whole Earth, it spans the ocean, the atmospheres, the ice masses, the solid Earth. It's a very complicated system, and in order to predict its behavior, we have to understand not only the atmosphere, not only the oceans, not only the ice masses of the Earth, but how these different components of the system interact.
And that formidable challenge of understanding the interactions of all the components of the global system is the business of the science of climate. Predictions of climate change are emerging from sophisticated computer models. But there would be no models and no predictions without a theory. And models and theory are no use unless they're tested against data from the real world. Data, theory and model are all essential, as a lesson drawn from the history of climate research shows. In the 1780s, there were a number of abnormally fierce winters in Europe. This unusual weather pattern kindled the interest of amateur scientists, the so-called Mannheim Group.
Their objective was to see if they could discover patterns in the weather. And they were forward-looking enough to realize that in order to achieve this objective, they would have to collect weather observations from a wide area.
These sorts of observations were not that very much different in principle from the sort of observations which weather forecasters use today to predict tomorrow's weather. Here we have across the whole of Europe observations taken at the same time of the day, several times a day, using a standard set of instruments and using a standard protocol. And you need to remember that these instruments, which were then being used to take these daily weather observations, they seem quite simple, in many respects rather elementary to us, but they were right at the leading edge of technology then. It was the space race of the late 1700s.
These people were working in the dark to some extent. They didn't have the advantage that we have today of the fronts and the air masses by which we can analyze synoptic charts. And I think to some extent they were disappointed because they were collecting all this information and they put it all together, but they were not able to see if there were any patterns emerging.
Now, the unfortunate aspect of the Mannheim observation network was that it was relatively short-lived for about 12 years, from the 1780s through to the 1790s. But for that period, we have real instrumental data.
So we can build on their endeavours now using modern techniques, using modern theory in order to understand the patterns more clearly.
The Mannheim Group recognized the fundamental need for accurate and reliable data, but they had data with no theory. Today we have more data, but now science has provided a theory, a model of the weather system. Fronts and anticyclones are individual weather events, which brings up the next question. What then is climate?
Climate is the
long-term average of all the weather events, if you like. So if we look at a period of 30 years or 50 years, if we then take all the weather that's occurred over those periods, the rainfall on a particular day, the sunshine, the warmth, or whatever it might be, including the extreme events, and we average those out over a long period, then that's what we describe as climate. But it's not just a single figure which says a long-term average of 10 degrees or whatever it might be. It also represents the variability that will have occurred during that long period on a day-to-day, a year-to-year, or a decade-to-decade basis.
So, climate is average weather. But what drives this weather system? Solar energy warms the Earth's surface, and this warms the air above. The air rises and moves away from the equator towards the poles. As it rises, the air cools, and then it sinks back towards the surface. This process is called atmospheric convection. These great convection systems drive the wind. But the atmosphere is only one factor contributing to the climate system. Another very important component is the ocean.
Most of the radiation coming onto the Earth falls in the equatorial regions, and that has to be redistributed around the globe. And that job is shared between the atmosphere and the ocean. Water is very efficient at storing and moving heat around. That's why you have water in your radiators at home and not air. You can store as much heat in the top 3 meters of the ocean as you can in the whole of the atmosphere above it.
Water in polar regions is cooled. Cold water is more dense than warm water, and so it sinks. In fact, cold water is continuously sinking in both polar regions. Meanwhile, the winds are driving the surface currents. The so-called gyral form of these current systems results partly from the Earth's rotation and partly from the shape of the ocean basins. If we look at the surface and deep currents together, we can think of them as a kind of global ocean conveyor system. It carries cold, deep water through all the main ocean basins and returns warm surface water back to the polar oceans, especially the North Atlantic. The atmosphere and oceans are intimately connected. Together, they're the main driving forces of the climate system. So how could humans really have an impact on such a gigantic global system?
Climate change has been a cause for concern for well over 100 years now. In fact, in the late 19th century, the Swedish scientist Arrhenius warned quite explicitly that burning coal could lead to global warming.
Arrhenius was one of the first to develop a theory of how humans could affect the global climate system, the theory now known as the greenhouse effect. Gases in the atmosphere allow shortwave solar radiation through to reach the Earth's surface, which heats it up. Energy is then re-emitted in the form of long-wave radiation. This long-wave radiation is trapped by the same gases which allow the shortwave radiation to pass. One of these key gases is carbon dioxide. So, have humans really had a significant impact on the climate? Has the greenhouse effect, enhanced by humans adding more carbon dioxide to the atmosphere, really brought about an increase in global temperatures? One way to find out is to compare modern data with older measurements.
This is BT number 1, Board of Trade number 1, which was the first thermometer of the Met Office in the 1850s. It was calibrated accurately to within about 0.1 of a degree, plus or minus 1.1 of a degree, and this would have been sent out to various places around the country so that they could then record accurately the temperatures for us in the Met Office. These would have been sent to the various places, and then they would have sent their data into the Met Office, and we would have started to plot them on these charts. And this is the chart for May the 23rd, 1867. Different charts that we have nowadays. This chart here has the various weather observations from around the country, like Portsmouth, London here. London, the temperature was 42 degrees Fahrenheit, the pressure was 30.04 inches, and there was a northerly wind. These charts, I say, started in 1867,
and we now have probably about 1 million charts going from 1867 right to the present day.
The millions of bits of data which reach the Met Office each day allow us to forecast the weather. But they also provide extensive evidence of changes in climate over the last century. The detailed records of the last century do show variation in surface temperatures. But is this change significant?
Well, we only have a good record of global climate extending back around 100 years. We know over that period that there's been warming of around 0.5 degrees Celsius, but we're not sure what happened before that point. What happened 200 years ago, what happened 300 years ago, what happened 1,000 years ago. So it's extremely important that we extend our records back further in time, because then we'll find out whether this recent warming trend is a new phenomenon, in which case we may well be responsible, or whether it's part of a longer-term trend, in which case it's more likely that it's a natural change, or at least part of it is a natural change in climate.
Is it possible that the climate was changing before humans created industrial pollution?
We're lucky to have a very interesting diary from Norwich, which was made by a local miller in the centre of Norwich, more or less, and he kept a regular...
We need more data. But how can we get data for periods before humans kept these detailed and systematic records?
I can mention straight away 1601, very, very cold over a very large area in the Northern Hemisphere. 1642, 1695 and a few years after that. 1032 was very, very cold, and maybe 1628 BC was majorly cold.
The best systematic and detailed human records take us back only a few hundred years to the invention of reliable scientific instruments. So how do you get a detailed and long-term record? If scientists can't rely on human archives, they have to look to other natural sources of data.
What you can see here now are wide and narrow rings. You can see quite clearly the year-to-year growth. What this tells us is really when the tree was growing well and when it was growing poorly.
But a tree that's living today can take you back only a few hundred years. This is surely no advantage over the human records.
Let me illustrate it with a piece of oak which was cut down in this region. And we know that the year it was cut down was 1983. And by measuring the rings back, we know there are 250, and this takes us back into the 1700s. The beauty of tree rings in this area, or in any area where there's a strong seasonality of climate, is that they only produce one annual ring, clearly each year, and that allows us to build a unique, absolute scale of measurement. Now, once we've got back in this sample, for example, and many more like it, to the 1700s, we can take another piece of wood, like this one, which may well have come from an old building, or even a very old dead tree, and we can do a similar measurement of the annual rings, and by matching this pattern of rings, the changes from year to year, with the changes in the original sample, provided we've got enough of an overlap, we can get a unique position, a unique match, which allows us to take this scale right back another 100, 200 years, say, and by using even older samples, such as this piece of oak, which came out of a German bog, and is in fact 2,500 years old, we can continue this record back even to earlier millennia. So given a several thousand year series, and in fact in some parts of Europe these series have been able to be extended back even 8,000 years and more, we then ask the obvious question, what can we tell about the past climate in this record?
Detailed analysis of the distances between the rings, their thickness and density provides a wide range of climate information.
We can find summer temperature. In some regions you can reconstruct annual temperatures. Simple rainfall during the growing season, rainfall even in the winter season. Because of the indirect relationships between temperature and rainfall which actually control the tree growth, we can reconstruct pressure data because it's that pressure data which controls those primary climate variables. We can even reconstruct sunshine records. The important thing is, though, that you can't get all of this information from the same trees in the same areas. the major bits of work that goes on in dendroclimatology is the sorting out of the different signals that the trees contain, and then using sensible statistics to try and reliably reconstruct that information back in time.
So, natural sources of climate data, like tree rings, show that climate has changed, at least on land. And these extended records are showing that climate has undergone significant and occasionally abrupt change over thousands of years before humans kept systematic records. Unfortunately, tree rings can take us back only to the last glacial period, when climate warming allowed the trees to start growing. But a few thousand years of tree ring data is nothing compared to over 4 billion years of the Earth's history. To go back even further, you have to look elsewhere.
This is a collection of sediment cores from the world's oceans. These cores are cores through the layers of mud and sediment, and the sediment type is very often controlled by climatic changes. Some of these sediments go back 500,000 years, and this forms a geological record rather than a human archive record. Here's an example of a core that goes back some 100 to 200,000 years. And the sediments within this show clear differences visually, which have been caused by differences in climate. Now you can see here a whiter carbonate ooze, and here a red-brown clay. These carbonate oozes have been laid down during interglacial periods, warmer periods, and these red clays have been laid down during the glacial periods, cooler periods. Now the sedimentation rate is about a centimetre per 1,000 years, so we might be looking at, say, over 10, 15 centimetres, 10, 15,000 years.
The clays on the seabed come from weathering and erosion of rocks on land. The white sediments consist mainly of calcium carbonate, which comes from the tiny shells of billions of minute plankton that live near the surface of the ocean. When the plankton die, their remains sink to the seabed. Examining the mix of different plankton species, the assemblage, can tell us a lot about surface temperatures where they lived.
In any one area, there is a mixture of different species in the plankton, just as there is a mixture of species of trees in a wood, for example. And so we can measure that, and we will know whether it's a tropical assemblage or a temperate assemblage or a polar assemblage, just as we would with plants on land or animals on land. And now it turns out that in the case of the plankton, there is a quantifiable relationship between the assemblage of plankton and the temperature of the water in which they grew. So by taking the assemblage and analyzing it, we can then calculate what the temperature conditions were in which those organisms lived.
So, climate data are available from a wide range of sources. Detailed chemical and physical examination of natural sources, like tree rings and ocean sediments, are proving to be a powerful extension to the short-term human records of the last few hundred years. What does the analysis of these long-term records tell us? Is the change over the last few hundred years really significant? When seen in a longer-term context, it's clear there have been other periods of significant climatic variation. These larger-scale variations over periods of tens of thousands of years are the glacial and interglacial periods of the last ice age. It turns out that the variations over the last few hundred years are really quite small compared to the massive changes that took place before. What could account for these changes? The theory has to include the role of the sun, the source of all the energy driving the climate system. The Earth is continually altering its position in relation to the sun, and so the amount of energy received can change. The angle of the tilt of the Earth varies, taking over 40,000 years to complete the move. At the same time, the axis behaves like a top. It takes around 21,000 years to trace out a full circle in the sky. Then there's the Earth's orbit around the sun. It changes from circular to elliptical, and back to circular, over about 100,000 years. But these aren't the only changes that take place. Other factors have to be put into a theory of climate change. Radiation from the sun changes on a much shorter timescale. One important change relates to sunspots. The more sunspots there are, the more radiation we receive from the sun. And there's a change in sunspot activity on a cycle of about 11 years. Scientists now know that the period of cold in Western Europe recorded by the Mannheim Group coincided with one of these more significant changes in sunspot activity. But there are other much less predictable causes of climatic change.
So there are scattered but fragmentary observations throughout the period.
And evidence of one of them lies in the Met Office archives.
In addition to the regular weather observations we had from the 1850s, we also have some older observations compiled by private individuals in the 1700s. This particular one is taken from Linden Hall in Rutland from 1777 to 1789 and is a particularly interesting one for June 1783. He makes some comment about uncommon smoky air for 10 or 12 days at the end of the month. Now what he meant by that is open to some speculation.
That smoky air has nothing to do with industrial pollution. The reference probably relates to haze produced by a volcanic eruption. The cold snap in 1783 was probably a result of low sunspot activity compounded by haze from the eruption of Laki volcano in Iceland. But are the sun and volcanoes the only natural causes of change? There's at least one important element missing. The greenhouse theory suggests that changes in carbon dioxide levels affect temperature. But pollution is only one source of carbon dioxide.
There is a natural cycle of carbon that's going on all the time. Vast amounts of carbon dioxide is being exchanged between the oceans, the terrestrial biosphere, trees and plants and so on, and the atmosphere. That goes on all the time and has been going on for billions of years. The carbon dioxide and water vapor that's already in the air already makes the Earth about 33 degrees warmer than it would otherwise be, and therefore it makes life habitable. What mankind is doing is burning fossil fuels, coal, gas and oil. The carbon in those fossil fuels is combining with oxygen in the atmosphere and creating more carbon dioxide, and it's unbalancing the natural cycle. An enhancement of the greenhouse effect by more gases going into the atmosphere will allow those temperatures to rise, and that's the focus of the concern.
In Antarctica, scientists have been looking into the snow for clues to changes in carbon dioxide levels. Air is trapped in falling snow. Over thousands of years, layers of snow build up, forming a record of the changes in the air over time. The ice cores show that carbon dioxide levels have been changing for many thousands of years. There is natural variation in the concentration of carbon dioxide. And when compared with the record of temperature change, there is an obvious correlation. But which is the cause and which the effect? We now have theories of natural causes of change, and we have theories of human causes of change. If these two theories are combined and run as computer models, they make predictions that should match the data. But do they?
There are natural factors which might have produced this warming, but we're now confident that in the climate response to this global warming, we are picking up, we are identifying the fingerprint of man's contribution.
So, is that it? Do we now understand the global climate and our effect on it? Not quite. The Mannheim Group's efforts and what they were unable to complete provide a vital lesson. Any scientific investigation requires the three elements of a theory, predictions from that theory, and testing by observation. The rigorous application of those three key elements has led the modern-day climatologists to realize their predictions weren't quite good enough.
When we ran the global climate model that we build here, when we looked at the climate monitoring, the actual observations, we saw about ½ degree. And we simulated the rate of change of temperature over the last 100 years. We ended up with a change of temperature of something like 1 degree Celsius that we would be expected to see. There was obviously a mismatch there, and that was a bit worrying. What was done here for the first time was to not only take account of the changing climate due to carbon dioxide, but to also look at another effect on climate.
We now know that there is a human volcano, that we're emitting into the atmosphere sulfur dioxide pollution, and this causes sulfate aerosols to be formed in the atmosphere, and they have a very direct effect on the energy balance. They're bright, they're shiny, they reflect the incoming solar energy back into space. But then there's a secondary effect, because they're also very powerful as cloud condensation nuclei. They create clouds, they form new clouds, and it just so happens that it's the kind of cloud that also causes cooling, that interacts with the energy balance and cools the surface of the planet.
When we incorporated those effects into the climate model, we immediately got a much better agreement between the observed temperatures that we've seen and those which were modeled by the climate model. And that was very good to see. It doesn't guarantee that we're getting it right by a long shot. There must be an element of luck in this, but at least it makes us a bit happier that we don't have the large sort of discrepancies that we had before.
The refined computer models reinforce the theory that industrial pollution is affecting the climate. But no theory and no model is ever complete.
It's the height of scientific arrogance to believe that we could ever simulate such a complex system in a computer model. We do our best, and we have to use all the tools of the trade in order to predict the climate future. So I'm not saying for a moment that we shouldn't be modeling, but we should be aware of the limitations of our models, particularly when we're using the results to guide policy.
Scientists don't have a complete theory of the climate system. There are still critical aspects of the system which need to be understood.
If we look at the global warming projections over the next 50 to 100 years, they suggest a slow, gradual, a steady change in climate. But when we look back over historical time, the past few hundred years, if we go back further into geological time and look at the record of natural climate change, we find that often the change isn't gradual, it's very abrupt. We have a very swift transition from one climate state to another.
One of these sudden changes, a shift in the pattern of ocean circulation, for example, could throw the northern hemisphere into an abrupt deep freeze. But the causes of such changes and our possible contribution to them won't be understood without further interdisciplinary research.
In many cases, scientists believe that they've got things just about right, and then surprises happen. So things happen in the atmosphere which remind us of our ignorance of a lot of the basic processes that are going on. And we do always have to have that at the back of our minds.
If we work together, we can get a much clearer picture of helping each other how to disentangle our own records. We can see how our different ideas support each other. We can get a good indication of when the data sets differ very strongly from each other. And in fact, it's only by using interdisciplinary science that we can indicate to ourselves and to the public how confident we are in the interpretation of our records.